That's not really this section. It's just review on doing implicit differentiation, because we were going to have to use that on our other problems. So, C is defined by xy equals -4. Which of the following statements is true of curve C at the point -2, 2? Okay, so you can see here that it talks about a first derivative and a second derivative in this on all of your explanations. So this is an example where you would use that second derivative test. And if we remember that second derivative test, our first derivative has to equal 0, and then we have to know the sign of the second derivative. So you could really, well, actually, this talks about maximum minimums. This talks about increasing and concave up, right, your concavity. So, so it just is going to depend on what we get for these derivatives. So if we take the derivative of x, y, Sarita, what would we do to take the derivative there? Good. And what would that be for this one? Almost, when we take the derivative of y, we will get 1, but we have to put with it dy dx. So we'll have x plus x times 1 dy dx plus y just times that 1. And derivative of -4 is 0, so that'll go away. So if we solve that for dy dx, we got x dy dx equals -y. We divide by x, so dy dx equals -y over x. So we only care about the point -2, 2, so we're going to plug that in. So it's multiple choice, so notation is not as important, but correct notation would be like this. That will show that you're plugging in -2, 2, and that will give you -2 over -2, which gives you +1. So we know our first derivative equals 1. That's going to rule out a couple options here. What answer choices are gone? A and B. So we're actually not using second derivative tests because there is not a maximum or minimum point here because we don't have the derivative equal to 0. We would, actually, I think, no, we can't. All right, so since our first derivative is positive, that tells us that our function is increasing. Both of these say increasing. Both of these say first derivative is positive. And that dy dx, I guess I should have used the y prime so my notation matched theirs. But that is our first derivative. Okay, so we've got 2 of them ruled out. Now we need to take our second derivative. So for our second derivative, we got to use the quotient rule. Connor, what will we get whenever we take the derivative here? Okay, good. And so if we clean that up just a little bit, we'll have -x dy dx plus y over x squared. And we need to plug -2, 2 into this here. You could take y over x and plug it in for your dy dx. But because we only care at the point, what I would do is I would do the second derivative such that x, y equals -2, 2 would equal, and then you're going to have -x, which is -2, times dy dx. Dy dx we just found on the last problem, or last part of this problem, right? We found that it was 1, and we're plugging in that same point, so we can just plug in 1 for that. plus our y, which is 2, over negative 2 squared. So that is going to give us 2 plus 2 over 4. So we get 1 for that also. And that is positive, so our second derivative here is positive, and C will be our answer. Okay, questions there? All right, so 3, we've got our function. They give us the first derivative. They give us the second derivative. We don't have to find those. So it says, which of the following statements is true about the curve in the fourth quadrant? Okay, so there are 2 of these that you can rule out from the very beginning if you look at your answer choices. What could be ruled out from the very beginning? A and B. Why? Perfect. That tells us increasing or decreasing. So these 2 are out because the reasoning is the first derivative, which only tells us about increasing or decreasing, not concavity. Now, if it said something like dy dx is increasing, then we would have to consider it. But the sign of the first derivative tells us increasing or decreasing, not concavity. So the second derivative is what we're looking at. Really, this first derivative here is just sort of there as a distractor to make sure that you know which one you should consider. So if we're in the fourth quadrant, what do we know about the signs in the fourth quadrant? Positive and then negative, right? X coordinate positive, Y coordinate negative. So I could plug in a specific number. I don't necessarily have to. My second derivative in that first quadrant, when I'm plugging in positive, negative, oops, let's make that to be a negative, not a negative 1. If I'm just going to consider what's going to happen there, I'm going to have negative 81, I'm going to put that negative up there on top, over 16 times my y coordinate is going to be negative, and I'm going to raise it to the third power. So without knowing the exact number, because all we really care about sign is, right? I'm going to get negative 81 over a negative number, and negative over negative, positive here. So second derivative is positive, curve is concave up. So C would be your answer there. Okay, questions on that one? All right. This one asks us at how many points on the curve in the XY plane does the curve have a tangent line that is horizontal? What do we know when tangent line is horizontal? Derivative equals 0. So we're looking for where the derivative equals 0, right? So we need to find the derivative here. So Wesley, what would we do to take this derivative here for this one? We don't have to use the quotient rule because in our fractions there, just the power rule, right? So what would we get? Perfect. Almost. It needs something with that second one because we took the dy dx. and that will equal 0 because the derivative of 9 is 0. So if we solve that for dy dx, we will have dy dx equals negative 2/3 x to the negative 1/2. Oh wait, I should still have my 2/3 y to the negative 1/3 here. We'll divide both sides by 2/3 y to the negative 1/3. Should be a 1/3. And so what's going to happen with that 2/3 and 2/3? They'll cancel and just be 1. You will still have the negative. I'm going to put that out front. And what should I do with those negative exponents here? I can switch them to the other side. So that gives me y to the 1/3 over x to the 1/3. And it might be helpful to think of it as the cube root of y over the cube root of x. All right, so I want to know, this is my derivative, I want to know when it equals 0. What is going to be equal to 0 whenever my derivative equals 0? The numerator or the denominator? Numerator. So I'm going to set that numerator equal to 0. I'm going to just cube both sides. Y is going to equal 0. This may lead you to believe that the answer would be 1 because you got one answer there for that, but it's only your y coordinate. So whenever we're dealing with things that are defined implicitly, they're not necessarily functions, right? So it doesn't mean that there's just one single point there. There could be 2 or 3 or 10 x's that go with it. So we want to take this answer and plug it back into the original to find the x coordinates. So we'd have x to the 2/3 plus 0 to the 2/3 equals 9, which that 0 is just going to basically go away. I'm going to write that as the cube root of x squared. So I could cube both sides here. And I'm going to do this. I'm going to leave that as 9 cubed. Because this would be calculator active. I mean, 9 cubed is not the worst thing in the world to do. But we're getting ready to square root that. So the square root of 9 cubed can also be thought of as the square root of 9 with the cube on the outside. What is our square root of 9? It's 3. And 3 to the 3rd, 27. But I did just square root both sides, so I forgot something. What did I forget? Plus or minus. So we should get 2 answers for this. So what you have here is you have the point 27, 0, because they got to go in pairs, xy pairs, and then negative 27, 0. So 0 is not a separate answer from the positive 27, negative 27. And that last one is basically like the same type of problem, which makes me think on the homework there's one that I didn't do. Let me pass this out. See if there's one maybe to look at. Thought there was an issue on this one, but I couldn't remember where it was at. Let me look through these. That one, we've already done one like that. I already did one like that. 4. Let's do 4. Alright, so from the homework paper, let's do number 4. I meant for one of these to be on there, on the notes, and not 2 of these. I didn't mean for 4 and 5 to be there, but obviously I didn't fix it. So let's look at this one real quick. Okay. All right. Given the curve y times 2 to the y power equals x in the xy plane, for what value of y, if any, does the derivative of y with respect to x not exist? So we need to remember something that we've probably forgotten. How do we take the derivative of 2 to the x power? In this case it's y, but it's not exactly chain rule. The rule is just different. So exponentials, e to the x, the derivative is e to the x, right? It's just itself. But if you have a different base, if the base is not e, your derivative would be 2 to the x natural log of 2. So we're going to need that rule to be able to take this derivative. It's actually the same rule for e to the x, but if we do e to the x natural log of e, natural log of e is 1, those cancel each other out, right? And you just get e to the x. So you could apply that same rule here. We just usually don't, because there's a more simple rule. Okay, so our derivative here, I've got y times 2 to the y. What do I have to use to take that derivative? Product rule. So I've got to do y times the derivative of 2 to the y, which is going to be 2 to the y times natural log of 2 times dy dx, because I just took the derivative of something that had a dy dx, or had a y with it. Plus 2 to the y times the derivative of y, which is dy dx. And that will equal the derivative of x, which is just 1. Short schedule. Alright, I forgot we're on a short schedule. So do the rest of those problems. If you don't get, try 4. You're going to factor out your dy dx. If you don't get all the way done with that one, that is okay. I think it's posted. I think. Let's see if that is true. I don't know if there is an answer key or not on this one. It might be a no.